Okay, so for the question two, we have this circuit again. There's different circuit, and the question asks us to have a 0 to 10 sensitivity resistance scale, sensitivity of the resistance scale, which can scale 2.5 kilo ohms per unit, and it asks us to plot a graph of the resistance versus knob scale using a previous circuit simulator, which is I use Tinkercad, and select 10 readings at knob resistance at scale of 1.1 to 10. So for this question, I'm using 2.5 as the minimum most minimum scale, and 25 kilo ohms 2.5 kilo ohms as the most minimum scale, and 25 kilo ohm as the maximum scale. And each of the scale, it can scale to 2.5 to 225. So we have uh 10 scale right here. So it's follow the question needs. So the first one, we can see how the circuit works. So you have a meter at the middle, and divided we have four resistors, which is basic resistance bridge configuration. And can now we can see how the circuit is being built. So first we have the commonly used are the batteries, and the three resistance, one potentiometers, and four voltmeter multimeter, and one and no sorry 3 voltmeter. So three multimeter that measure voltage. One measures resistance. I'll tell later why we use a resistance checker, and the other one is for the current. And okay, so basically this circuit I've divided into two parts. So for the first part, we have the top parts right here. So the positive terminal of the batteries go to one leg of the potentiometers, and the wiper or the middle pin goes into the 150 ohm resistors, which we can see right here in the questions. And the leg of the resistors is connected to the negative terminal of the batteries. This is for the top parts, and for the bottom parts, we have the positive terminal of the batteries is connected to the 59 kilo ohms resistors, which is right here, and the leg of the 59 kilo ohm resistors is connected to the bottom to the right side of the resistor, which is 330 ohm resistors, and we have its leg is connected to the negative terminal of the batteries. So this is basically the configuration of the circuit. This is basically how we build our circuit for this question. Quite simple, quite clear. And okay, so for the next one, I want to explain the manual calculation first, and then go to the simulation. So for the manual calculation, we use because as we know that so for a balanced wisdom bridge. So in order for the wisdom bridge to be balanced, we need to know that VA, the voltage at A, top part of the top part of the circuit, and the bottom part of circuit must be equal. So that's why the top part must equal to the bottom part. So that's why we can see that the voltage in the bridge is zero, and the current in the bridge is zero. So for the balance wisdom bridge formula, we can see that the ratio of the top branch resistors must be equal to the ratio of the bottom branch of the resistors itself. And we can see that how to calculate the potential for resistance is simple. So basically, we just with algebra, and we can get that our resistance for potential is equal to 17.73 kilo ohms resistors. So for scale, this is given in the question, which it says that each of the steps or each of the scale need to be scaled for 2.5 kilo ohms. So we take 17.73 kilo ohms divided by 2.5, and we can see that 7.09 is being calculated. This means at the seventh scale of the potentiometer, the Wheatstone bridge will be balanced. So we can see that the voltage at bridge right here will be zero, and at the voltage at A, the I at sorry, no, the voltage bridge will be zero, and the current at bridge will be zero. So we can see, so okay, so this is example. If this is where I put 25 kilo ohms for the potentiometers. So this is the readings of the voltage bridge. So this is the voltage bridge, negative 21.8 millivolts. So for the I bridge, we can see is negative 45.8 microamperes. Very small values, um, very small, very small currents and very small voltage. So why is negative? Because the voltage as at A is smaller than the voltage as B. That's why, because VA minus VB equal to, because the formula is VA minus VB, so we can see that VA is much smaller than VB. That's why we get voltage as bridge is equal to 0. And okay, so for the next thing, we can see that all of these are the results that I've taken. So let's see some simulations. Okay, so why did I use a resistance checker is basically I want to check whether how much resistance in this potentiometer. So basically I will just connect to the potentiometer and run a simulation. So right now I want to change to 17.5. Let's say we want to run at 17.5 kilo ohm. Okay. So according to my calculation, this is where the bridge is balanced. So my expected output should be the voltage at bridge is equal to 0 and the current at the bridge is should be equal to 0 too. So we start simulation, we delete the wire and we reconnect the circuit. So the positive terminal of the battery is connected to the the right pin of the potentiometer, and the middle pin, which is the wiper, is connected to the 150 ohm resistors, which is the top part. So after this, we can run our circuit. Yep. So we can see that the voltage bridge is equal to 0 as we expected because we calculate when the potentiometer is at 17.73 kilo ohm, the bridge will become the Wheatstone bridge or the circuit will become balanced. So we can see that the voltage B is 75.5 millivolts and the voltage is A is equal to around 76.5. So difference will be around 1 millivolt. But Tinkercad has how do I say it it changes value. It's not like because Tinkercad the simulator like to choose the close value, so that's why it choose 0. So in this case, the bridge is balanced, the circuit is balanced, so we can see that 0 volt is being C at voltage bridge. So next we can see our current at this point. So I may just this connect the circuit. So this is the voltage A, this is the voltage B, top part and the bottom part. So we can run a simulation, see how it sits. Okay, so see the current is 0, which state that the circuit is in balance mode. And it uh and this is what we expected because the circuit is balanced, no voltage, so voltage bridge is 0 and voltage ampere and the current ampere is the current is 0. So yeah, so that's why I'm using this resistance to check on how many resistance does this potential currently have. So I can delete this. Okay, let's see if I want to check another how do I say another resistor value. So we can run first, and maybe we can try to run 12.5. Okay, so we can delete and we can reconnect back circuit. reconnect back the circuit. Okay, we can start running. So this is the value. So the reason why voltage B didn't change is because of the configuration of the circuit itself, because we can see that voltage B is having the constant resistance, which is 39 kilo ohm and 330 ohm resistors. This value doesn't change. That's why we can see that the VB didn't change throughout our simulation, is because resistance didn't change for VB. This is expected. And go back to so this is the simulation. We can see that everything is working fine, everything is working good. So we can stop it. Right. So that's the simulation, and now we can go to the results. So for VA, it's um getting decreased. For VB, it's constant because so resistors is constant, it didn't change. For bridge, also decreasing, and at some point at 17.5 kilo ohm, it becomes zero. This is where the circuit is balanced. So for graph, we can see that the resistance versus knob scale, simple graph, linearly. So the knob is increasingly linearly with the potential, the resistance. So we can see the straight line going up. This is for resistance versus knob scale. But for bridge voltage versus potential resistance scale, we can see that I'm using scatter plot here. It's easier for us to see. This is inversely proportional, going down decreasingly. So our pot or potentiometer resistance is inversely proportional to the voltage at the bridge. Same goes for bridge current versus potentiometer. The potentiometer for resistance is inversely proportional to the currents, to the bridge currents. So we can see that it's decreasingly going down. Just like in this table, we can see right here, V bridge is inversely proportional to the potential to the resistance, and also the current bridge is inversely proportional to the potentiometer. And lastly, we can see that for numerical calculation and also the simulated calculation, we can do some error. We can see the error is around 1.3%, quite small, which is we can conclude that the simulation and also the calculation is quite similar in terms of value, in terms of accuracy. So for the final calculation of these two assignment is that the circuit was for the first assignment we can see the circuit was successfully analyzed using both manual calculation and simulation. We can see that IA, IB, IC, BA, and VB were very close to the manual calculation result. This shows that Ohm's law, parallel regression, and Kirchhoff current law were verified through simulation. So for the second question, for this question, potentiometer was varied from 2.5 to 225 kilo ohm according to the scale that the question asked, which is 2.5 per unit scale. On the graph of resistance versus knob scale show a linear relationship which we can see. Right here is going up linearly. Uh, for the bridge voltage and bridge current decrease from cross near zero. So from the simulation, the bridge balance is occurred around, I think 17.5 that we see just now. At this point, the voltage bridge is equal to 0 and R bridge equal to 0. So my calculation gave us the battery resistance as around 17.73. Quite not is not as accurate in the simulation, but very close. So the difference is only around 1.3%. The small error may be due to the cat rounding the potentiometer. Yeah, just like I said, um, the simulation and in Tinkercad, they like to round out the number. So that's why we have slightly different answer for potentiometer for our manual calculation and also our simulation calculation. So therefore, the simulation result agrees well with the manual calculation and the bridge balance condition was separately identified. So I think this is my second question, and thank you very much.